Good morning. So now let us see the effect of bypass capacitor on the gain. In the frequency response curve itself, we have seen the effect of bypass capacitor. At very low frequency case, the gain fall you can observe in the frequency response curve. This is due to coupling capacitors and bypass capacitors. With reference to coupling capacitors, we have seen the equations for the gain and also corner frequencies. Similarly, with reference to bypass capacitor, how the gain should be and what about the corner frequencies that we are going to see now. First of all, tell me why the bypass capacitor decreases the gain with the reduced frequency. That means the purpose of emitter resistor is actually to it stabilizes the operating point, but when you apply the signal for amplification, because of AC negative feedback, the gain should be reduced. So that to avoid that AC feedback, a bypass capacitor is connected in parallel to RE. Okay. So but at the very low frequencies, this bypass capacitor CE offers very high reactance. Therefore, at low frequency case, the AC feedback can be presented so that the gain is reduced. Now let us see the effect of this emitter bypass capacitor mathematically. Okay, so here is the diagram showing bypass capacitor in parallel with RE and the corresponding equivalent circuit also shown. In the equivalent model, the VCC or V plus and V minus both are at ground. Therefore, the resistance RC is connected between output terminal to the ground, and transistor is replaced with the hybrid pi equivalent model, including without considering the early effect. And between emitter and ground, there is a parallel combination of RE and CE. Okay, so this is the equivalent circuit. Considering the bypass capacitor. Okay, so whatever we derived the voltage gain, input impedance, output impedance in the first unit, there we are neglecting all these capacitances. Okay, but now if actually in practical way you need to consider those capacitive effect also. Okay, or that analysis is generally in the mid frequency range. In the mid frequency range, none of the capacitor affects the gain. Okay, only at very low frequencies and very high frequencies the capacitance affects the gain. That you observed in the frequency response curve. In the middle frequency range, the gain is constant, whereas at very low frequencies and very high frequencies, the gain fall you can observe. Okay, now including this CE capacitor in parallel with RE in the equivalent circuit. Now see the analysis here, just deriving the gains. Okay, so first of all, let us find the IB equation. So IB is VI divided by the resistance. The resistance is including the different resistive components like RS plus R pi plus 1 plus beta times of the impedance, total impedance in the emitter terminal, that is RE parallel 1 by SCE. Okay, this is the total resistance, or this is the impedance in the emitter terminal. At the emitter, you have two components, RE and capacitor are in parallel. Therefore, the impedance is the parallel combination of those two. Right? This is the total impedance. Right? And if you see the output voltage, where the control voltage V pi is, in the diagram itself you can see that is IB into R pi, and the output voltage from the circuit itself, it is minus GM V pi into RC. Now substituting the V pi as IB into R pi, and I by is the above equation, so that the voltage gain V0 divided by Vi in terms of S. Okay, that is S is where S is the complex frequency notation. Okay, that is the transfer function in terms of frequencies. The transfer function in terms of frequencies. Okay, the transfer function means the voltage gain output to input voltage in terms of frequencies. Okay, so therefore minus gm r pi rc divided by rs plus r pi plus 1 plus beta times of re parallel 1 by sce. Okay, so this is the voltage gain we derived including the emitter bypass capacitor. Now if we expand this parallel connection, the AV becomes like this. The AV is like this. Okay, this is the AV. If we expand that parallel connection of RE and 1 by SC. Therefore, you can express the voltage gain in terms of time constants. In time constants, we can express it as like this. This part of the expression into the rest of the part represents 1 plus tau as or s tau a divided by 1 plus s tau b. In terms of time constant, you can express like this. Okay, where this part represents the magnitude. Okay, this part is represents the magnitude of this gain, maximum value. Where tau a is, what is tau a? This is product of RE and RCE. Product of RE and CE. Whereas tau b is this part, RE of RS plus R pi into CE divided by RS plus R pi plus 1 plus beta times RE. Okay, tau a and tau b you can express like this. Okay, and if you see the gain expression with reference to very low frequency and with reference to very high frequency, how it will be is, so when the frequency is approached to 0, that is at very low frequencies. At very low frequency, what happens? The bypass capacitor acts as a open circuit. Therefore, the RE resistor is included in the gain formula. So that the gain is, you can express it like this: Gm R pi RC divided by RS plus R pi plus 1 plus beta times RE. Suppose if the frequency is increased to very high value, suppose if omega tends to infinity, the RE resistor is not included in the gain expression. Why? Because at very higher frequencies the capacitor acts as a short circuit. Since it is in parallel with RE also acts as a short circuit. That's why RE is not included in the gain. So that the magnitude of gain at very high frequencies you can express as Gm R pi RC divided by RS plus R pi only, because RE resistor is not included now. It is short circuited. Because of bypass capacitor. Okay, so it is the gain formula at very higher frequencies. This is the gain formula at the lower frequencies. Okay, and with reference to this, the corner frequencies you can define in terms of tau a and tau b as. Reference to tau a, the corner frequency is Fa equal to 1 by 2 pi tau a, whereas due to tau b, the corner frequency you can express as 1 by 2 pi tau b. Okay, two corner frequencies you can observe, one at very high frequency, not very high frequency, one with reference to tau a and one with reference to tau b. So therefore in board plot you can show these two corner frequencies like this. So this is a board plot. At higher frequencies the gain is this much. Okay, with the increase in the gain with frequency, the gain is this one. Okay, that is the magnitude of AV when omega tends to 0. That much of is the maximum gain you can plot here, whereas at omega tends to 0 the gain value is this much. Okay, so we join this, the gain is slope is like this in between FA and FB. Okay, where FB is the corner frequency with reference to tau B and FA is the corner frequency with reference to tau A, right? So this is the effect of emitter bypass capacitor in the amplifier. Now analyze, okay, analysis is over. Now derive the corner frequencies with reference to emitter bypass capacitor circuit with the given following values. Okay, you solve this problem. Okay, so in the next class you can see the high frequency analysis of BJT and FET amplifiers, right?